final section of Chapter 6 is LHospitals Rule. And the LHospitals Rule is a way to handle limits. Limits that when we plug our number in as we are approaching a particular number, we end up with the result of 0 over 0, infinity over infinity, or 0 times infinity. And these are called indeterminate cases. You see that word right here. Indeterminate cases, because being really close to 0 over really close to 0, I don't know what that is. I can't determine what that is. I need another tool, and we have some tools in the toolbox. We have things like conjugate and common denominator and factoring and things like that. L'Hopital has got a way to handle this that might be a little bit more efficient than using any of those other tools that we have in the toolbox. So let's take a look at solving limits that result in a 0 over 0, an infinity over infinity, or a 0 times infinity. Because remember, we're only approaching these numbers. We're not actually ever reaching them. We're only close to 0 times close to infinity. All right, what did L'Hopital, this French mathematician, have to say? Well, L'Hopital says if we're looking for this particular limit right here, and it results in one of these 3 indeterminate forms, then what you can do to resolve that is to take the limit still as x is approaching a, but find the derivative of the numerator divided by the derivative of the denominator. This isn't quotient rule. This is derivative of the numerator divided by derivative of the denominator. And that may help you determine what 0 over 0, infinity over infinity, or 0 times infinity is. Well, let's take a look. What is the limit as x approaches 0 of the sine of x divided by x? The one thing, if you're doing a free response question, you're not allowed to write that this is equal to, those of you who know the unit circle know that the sine of 0 is 0. And x is going to be 0, because that's what x is approaching. Okay, we're not allowed to say that. If we're doing a free response question and we want to justify why we are going to use L'Hopital's rule, we're going to say this. We're going to say the limit as x approaches 0 of sine of x equals 0. We're going to say the limit as x approaches 0 of x equals 0. So you're not saying that the top is 0 and the bottom is 0. You're just saying that you're approaching them. And AP finds that as an acceptable way of saying, okay, this is why I'm using the L'Hopital's rule, because each of these limits is 0. So now we're actually going to use L'Hopital's rule. We're going to find the limit as x approaches 0. And we're going to take the derivative of the top, and the derivative of sine is cosine of x, divided by the derivative of the bottom, and the derivative of x is 1. And so now, if I put my 0 in place of being x, that I've got the cosine of 0, students who know the unit circle, divided by 1, that's equal to 1. So this indeterminate limit, because it was 0 over 0, we have now determined that limit is equal to 1. All right, down here. Limit as x approaches 1. Well, let's see. I would say if I'm doing this in a free response question. Now, if this is a multiple choice, you don't worry about this stuff. But I'm going to take the limit as x approaches 1, natural log of x. And I know that the natural log of 1 is indeed 0. I'm going to take the limit as x approaches 1 of x minus 1, that is equal to 0. And so I've now justified why I am about to use LHospitals rule. I'm going to find the limit as x approaches 1. And I'm going to take the derivative of the top, which is 1 divided by x, divided by the derivative of the bottom, which is 1. And now, if I put this 1 in place of that x, I'm going to get 1 over 1 divided by 1, which is 1. Not coincidence that they both came out to be 1. They aren't always going to. Let's go to our second indeterminate case. What if we get a limit where the numerator and denominator both approach infinity? Now we can see that happening here. The limit as x approaches infinity of e to the x over x squared. Now, I'm going to treat this like this is a multiple choice. I think I made my point that if it were a free response, I'd have to show that the limit of the top is infinity, the limit of the bottom is also infinity. Okay. So now I'm going to take the limit as x approaches infinity, and I'm going to find the derivative of the top, and the derivative of e to the x is e to the x, divided by the derivative of the bottom, which is 2x. And now if I have x approach infinity, it looks like the top is still really, really big. So is the bottom. If that's the case, I've still got infinity over infinity, and I need to L'Hopital a second time. I will take the limit as x approaches infinity, and the derivative of the top is still e to the x, but the derivative of the bottom is now 2. Now, as x gets huge, e to the x is huge. And what is huge divided by 2? Well, you might say it's half of huge, but yeah, this is going to keep growing and growing and growing without end. And so we no longer have a situation where it's infinity over infinity, but the answer is infinity. Let's take a look at another one. Again, limit as x is approaching infinity, and the top going to be approaching infinity. The cube root of huge is still huge. So we've got a limit that we cannot determine what the value of it is. So I'm going to follow my friend L'Hopital, and I'm going to take this limit as x approaches infinity, and I'll take the derivative of the top divided by the derivative of the bottom. Now I better think about this. And I better think of the bottom as being x to the 1/3. And so the derivative of that will be 1/3 x to the negative 2/3. Or 1 over 3 x to the 2/3. Well, before I even try to put infinity into this, I realize this is a fraction with 4 different values to it. I'm not doing it. I'm going to instead say, okay, I'll take the limit as x approaches infinity. But I'm not going to divide by a fraction. I'm going to take my numerator, 1 over x, and I'm going to multiply by its reciprocal. I'm going to multiply by the reciprocal of the denominator. And that would be 3 x to the 2/3 over 1. And I can probably simplify that further, realizing that this is an x to the first, I can say this is the limit as x is approaching infinity. And on the top, it's certainly got 3. But where does the x belong? Does the x belong on top or on the bottom? Well, when I resolve this x to the 2/3 on top and x to the 1st on the bottom, I see that the exponent in the bottom is bigger. The exponent in the bottom is bigger by 1/3. So let's see, what do we get? As x gets huge, what's the cube root of huge? Still pretty big. And 3 divided by a really, 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 really big number, going to get close to 0. So, yeah, you know what? With L'Hopital, there was a lot of manipulation that was involved here. Nothing we haven't done before, but more manipulation, the more places there are to possibly go wrong. So we've got to be organized. We've got to show our work. And I think we can work our way through this and see why this limit, as x approaches infinity, ends up being pretty darn close to 0. All right, we have one more indeterminate form. And L'Hopital just says take the derivative of the top and divide it by the derivative of the bottom. There's no top and bottom when you look at this third case. And so my instructions to you say we have to turn this into a fraction. Well, you know what? I'm gonna come down to the second example on this slide. Let's do this one first. Now, if x is approaching infinity, which it is, this number is going to be really, really big, and e to the negative infinity is pretty darn small. So again, if I were doing a free response question, I'd have to say the limit as x approaches infinity of x is equal to infinity, and the limit as x approaches infinity of e to the negative x is 0. Free response, I've now earned a point because I've justified why I'm using L'Hopital. But I need this thing to be a fraction. So I'm going to rewrite the original problem. I'm going to say the limit as x approaches infinity. And wouldn't this thing be unnatural to go down to the bottom? You've already got a negative exponent. Why don't we call this x over e to the positive x? I've already justified why I'm using L'Hopital, but if I now look at x approaching infinity, I've certainly got a huge number on top and a huge number on the bottom. And so I'll L'Hopital this. After I've turned it into a fraction, I'll say the limit as x approaches infinity. And the derivative of the top, derivative of the bottom. Okay, x is approaching infinity. You've got 1 over a huge number, and 1 over a huge number I haven't seen one of these on an AP exam, but I can't say it'll never happen. But if you do have a limit that approaches 0 times a limit that approaches infinity, we've got to turn it into a fraction. Not difficult to see how to do that in that final example. But what about this guy? This guy's a little tougher. We're approaching 0 from the positive side. So obviously, this thing has a limit of 0-ish. Getting pretty darn close to 0. But let's think about natural log. And natural log, as we approach 0 from the positive side, look where it's going. That guy is going to have a limit of negative infinity. And so this falls under indeterminate case 3. So I got to turn this into a fraction. I got to take the limit as x approaches 0 on the positive side. And I got to put one of these guys on the bottom. But there isn't a real natural way to do that, like there was in the previous example. I got to form a fraction. Well, I'm going to show you how to do this, and hopefully this will be reasonable to you. Natural log, I'm going to keep you right where you are. You're right up here on top. But this x to the first could be driven down to the bottom as x to the negative 1. X's are pretty easy to move that way. If you want to drive it to the bottom, just make the exponent negative. All right, we've already explained why this is a L'Hopital problem. We have now turned this into a fraction. And so now it is derivative time, where L'Hopital said we should do it. We'll take the limit as x approaches 0 from the positive side. The derivative of the top divided by the derivative of the bottom. That would be negative 1 x to the negative 2, which maybe I initially write like this. And then I take my eraser and say, wait just a second. Maybe instead of writing x to the negative 2, maybe I'll say it's over x squared. And like we've seen in a previous example, we now have a fraction with 4 levels to it. And I'm not touching it with a 10-foot pole. I'm going to instead, dividing, I'm going to multiply by the reciprocal. So I've got 1 over x times x squared over negative 1. And when I resolve this, I'll be taking the limit as x approaches 0 from the positive side. Looks to me as if the exponent on top is bigger. The result is going to be negative. I think we can see that because of this negative 1 here. So the result is going to be negative. The x is going to belong on top. On the bottom, we'll just have a 1. And if x is approaching 0 from the positive side, I'm going to have really close to 0 divided by 1. And what's a really, really tiny number divided by 1? Well, it's really, really tiny. It's very close to 0. The fact that it's negative really doesn't change anything. I am getting very, very close to 0. Apparently from the negative side, okay, because of that negative sign, but I'm getting really close to 0. That's the number I'm approaching. And so that's what this limit is equal to. Like I said, we don't run into a whole lot of indeterminate case 3. Most of what we see is indeterminate case 1 when it comes to the AP exam. Okay, hope that explanation sits pretty well with you. And after you have a little bit of practice on your assignment, you have a better feel for it.